Take our knowledge of Taylor polynomials and extend it to series. Okay? Let's talk about our Taylor polynomials. How did we create them? How do we create Taylor polynomials? Explain to me the process. Okay, you take the function, you take however many derivatives you need. What do you plug into all of those? The center. And then you create your Taylor polynomial based on the pattern.
Yes.
Right?
Yes.
Okay, what we are going to do is take those polynomials and make them series. Okay? So, each term in our polynomial looks like this. Whatever derivative evaluated at the center over k factorial times x to the k. If it's centered at something else, x minus the center. Okay?
Equals 0.
Yep. I'll turn the light off so you can see a little bit better.
This is going to get us really accurate. Is that why we use? No. Is that like a K? We've done the class. Wait, is that not before? Oh, that. Is that K?
Yeah, it's like the k derivative.
Okay. Is that really 20? Is that a 1?
I mean, I haven't really shown you anything new.
K's.
All I've shown you is how to take a polynomial and write it as a series.
No, are those n's? Are there n's somewhere?
Everything is just they're tick marks.
They're tick marks until here it's an n because we're going from 0 to n.
What's the glasses? Where's the glasses?
Okay? Now, this is the nth polynomial, right? Once we make it into a series, instead of n, what are we going to write? False. Infinity. Once we make it into a series, that n on the top of our summation is going to be infinity. Okay? Okay, but essentially what we are going to do is we are going to write series based on what you see to the right. Or actually write them both ways, I guess I should say. Okay. But what we'll do is to make them infinite, we'll just write like the ellipse plus dot 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 to imply that it's going to infinity. Okay.
I have 3 credits.
Why not? But we're going to get like last week.
Austin, you don't even have to worry.
No, well, my family does because we have to leave for my sister's graduation. And they don't want to.
Oh, yeah, you're younger.
They don't want to wait here for.
And both of your younger siblings are here, right?
Yeah.
And is there another one? Or like, is the freshman the youngest?
Yeah.
Okay. Okay. Okay.
They might skip 2 days.
If we're talking about a series, okay, so this is all I want you to do. All right? Change that n to an infinity, and then just write plus dot dot dot. okay? And now we have series.
The last one was
So this is the nth polynomial. Here, just change it to infinity and write plus dot 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 at the end. And now we have a series. This is going to keep going. You see what I mean?
yes.
I think.
No. I'm not seeing
So before we were just
So here we were stopping at n.
it.
For a series, it's an infinite series. We want to go to infinity. So erase the n, write infinity.
Oh, I just wrote infinities on the first one.
So then write plus dot dot dot.
Alright.
All right. So this is going to be fun. We're going to go through one example, and then I'm going to show you the 3 series that you have to remember to make your life easier. We like simple, short, right? We don't want to take more work than we need to. So I'm going to show you some shortcuts. Okay? Are you rewriting all this down?
Yes.
Yeah.
Why?
I don't know. Helps me memorize stuff. No, but it's almost like I just copied it.
Yeah,
Yeah,
that's
so we can move on.
that's
It's fine.
what. So just come back later, okay? All right, so we are going to write the Taylor series for our function e to the negative 2x with the center at 0. So technically it's a Maclaurin series, but I called it a Taylor series centered at 0. That's the definition of a Maclaurin series.
Same thing.
Tomato, tomato.
It's the model, by the way. Like I was curious the other day, like who actually goes around saying tomato?
I don't know. Probably someone that's not from the Midwest, okay? All right, so our function is e to the negative 2x. Our derivative. Okay, so evaluate at 0 would be what?
1.
Okay. Our derivative, negative 2 e to the negative 2x. Evaluated at 0. Our second derivative. I now can tell you know a pattern. Okay? So I would say, and sometimes they'll tell you, you want to get at least to like x cubed, x to the 4th. Okay? Sometimes I'll say find the first blah 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 non-zero terms and the nth terms. Okay? But do we know what the next one's going to be?
Yes.
Okay. So our function we know is going to be 1 minus 2x plus 4 over 2 factorial x squared plus, what's the next one? Try again. Negative 8 over 3 factorial x cubed. What's the next one?
16.
Okay. Do you think we can find this pattern? Okay. Let's talk about it. We have 1, negative 2, 4, negative 8, 16, blah, 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 blah. How do we write that? That's horrible. You agree? Thanks. Okay. How do you feel about said, negative 2 to the n
I like it.
over n factorial x to the n. Okay, we figured out that pattern, right? So this is what we're going to do. F of x is the sum from n equals 0 to infinity of negative 2x to the n power over n factorial. Bam, there's our Taylor series. Are you okay with me putting negative 2 and x together? Because they both have the power of n.
Yeah.
Okay, now that we've done that example, let me tell you about the 3 functions I need you to remember to make these Taylor series go more smoothly. We know the derivative of e to the x, 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 right? Okay? So let's talk about e to the x as a Taylor series. Series that we need to know. E to the x. We know each derivative is going to be what? This. And if these are centered at 0, each derivative is going to be the value of 1. So we would have 1 plus x plus x squared over 2 factorial plus 1x cubed over 3 factorial plus 1x to the 4th over 4 factorial. Are you catching my drift here? You need to know that. You need to know that e to the x is the sum from n equals 0 to infinity of x to the n over n factorial. I'll show you what we can do with that here soon. It's probably the easiest one to remember too.
Do you want me to put this?
Yes. So there are an infinite number of terms in between. Yes. Cosine of x. Cosine of 0 is? Okay, cosine of 0 is 1. And then the derivative is 0. Then the second derivative is negative 1. And then the third derivative, 0. The fourth derivative, positive 1. The fifth derivative, 0. The sixth derivative, take a guess. Okay, since sine and cosine, you know, we alternate with our derivatives, right? We are missing every other term. Did I miss you over here?
No.
We are missing every other term. So first of all, we notice that we have 1, negative 1, 1, negative 1 with the terms that we actually do have. So we would want negative 1 to what power? Okay. And then we have x to what power? False. 2n. Yep. Over, we only have the even factorials. Okay. So, our cosine of x power series is the sum from n is 0 to infinity of negative 1 to the n x to the 2n over 2n factorial. What? what will help you remember, cosine has all the even numbers. Alright? What do you think is going to happen with sine? Sine's going to have all the odd terms. Okay? Let's look at it. Okay? The sine of 0 is 0. Our derivative is cosine. Evaluated at 0 is 1. Derivative of cosine is negative sine. 0. Derivative of negative sine is negative cosine. The pattern's going to keep going, right? The next derivative is it negative, nope, it's positive sine. Sine of 0 is 0. Next derivative is cosine. Okay, we've seen both of these before, right? You've noticed how we're missing every other term because of the sine cosine derivative. Okay, so let's put this in general form. Okay, we're still going to have that negative 1 to the n with the terms that we actually have, but this time we have the odd exponents and the odd factorials. So we're going to have x to the 2n plus 1 over 2n plus 1 factorial. Because if we start at 0, that's how we're going to get the 1. Okay, so the sine of x is the sum from n equals 0 to infinity of negative 1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. Okay? Essentially what you're going to have to keep straight is which one is which. Which one are the evens, which one are the odds. They're set up exactly the same. Okay? Easiest way to figure it out is to plug in 0 to cosine or plug in 0 to sine. Is it 1? Is it 0? That's how you know where to start. Okay? So, why am I making you remember these? All right? It's going to help us when we have functions that either incorporate this or something is plugged into one of these. Okay? For example, okay, we can substitute into a series for x. I'll show you what I mean by going back to the very first example that we did. Okay, we have a shortcut for e to the x, right? Okay. Our shortcut for e to the x was x to the n over n factorial. What was our first example? E to the negative 2x. All we have to do, instead of x, we have negative 2x. No need to actually take all those derivatives. Was that our answer for our first example? It was. Not slick? Which makes it good, right? Okay. You can multiply or divide the series by a constant or a variable such as x. Okay. We're going to do an example here pretty soon of x cosine of x. Okay. You are allowed to add or subtract two series. We've already done that before. That's not new. Okay. Another, not new piece of information. We can differentiate or integrate a series. And like we've been doing the past 2 days, we can recognize a series as a sum of a geometric power series. Okay, that's what we did yesterday and the day previous. Okay. I am going to tell you that the expanded out version of the series are what you're going to be working with mostly. Okay, so the rest of the time, I'm not going to write the sigma anymore. We're going to talk about individual terms. So like the first 3 or 4 non-zero terms and then the general term. When I mean general term, that's when we write a term in terms of n. Okay. Get in the right spot.
Somehow
Did you put yourself there or the... Just don't want to do that close to Isaac. Okay, so we have 3 examples, and that's probably going to take us to the bell. Okay? Where is the time gone? Good. All right, here we go. First example. F of x is the sine of x squared. We know that the sine of x is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial all the way to negative 1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. Okay? You don't need to write that down. You already have that written down. All we have to do is for the sine of x squared, wherever there's an x, make it an x squared. So this would be x squared minus x squared cubed over 3 factorial plus x squared to the 5th over 5 factorial minus x squared to the 7th over 7 factorial. All the way until negative 1 to the n, x squared to the 2n plus 1 over 2n plus 1 factorial. Okay, so our power series for the sine of x squared, all we have to do is just work with some exponential rules. X squared minus x to the 6th over 3 factorial plus x to the 10th over 5 factorial minus x to the 14th over 7 factorial. Our general term would then be negative 1 to the n, x to the 4n plus 2 over 2n plus 1. Pretty slick, right? It also makes it nice because you don't have to think about what is this pattern, x squared, then x to the 6th, so 2, 6, 10, 14. What is that sequence? You don't have to worry about that. We can just use exponential rules to come with that 4n plus 2. Yes?
So when we do this, do you want us to do like those, or do you just want us to do like the sigma and that? Is it supposed to be affecting the next week?
Right now I want you to do like the terms with the general term. I will give you specific instructions as far as give me the first so many non-zero terms and the general term, or like write it as a sigma. Okay. Example 2 of 3. You're going to find on the AP test they want it more like this. That's what I'm trying to do. Suggestions. What'd you say? Okay, so this is x times cosine of x, right? So we have x times, our cosine was 1 minus x squared over 2 factorial plus x cubed, no, x to the 4th over 4 factorial minus x to the 6th over 6 factorial. All the way, our general term was negative 1 to the n, x to the 2n over 2n factorial. Let's see. So, all we have to do is multiply that x through. Once again, instead of trying to find a pattern, all we have to do is take our general term, x times x to the 2n becomes x to the 2n plus 1 because we just have to add the exponents together. Yeah, this isn't so bad. No. You guys all look like you're exhausted.
We really just never
Yeah, we haven't had one.
You guys have been spoiled. Okay, last example. Spoiled.
Last year was really bad.
Please do not, if you answer that phone.
It's important, they're giving me money. He's calling.
Okay, suggestions about what to do here. Split. Maybe multiply by 2. Well, like we want the representation of h of x, so that 2 has to stay there. But we can save it for the end, right? It's not like an equation, it's more of an expression, okay? So we know what e to the x is, right? We know e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial, blah, 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 blah. Okay? And we're going to add that to e to the negative x. Well, e to the negative x, we just plug negative x in. So that becomes 1 minus x plus x squared over 2 factorial minus x cubed over 3 factorial, right? All of the odds would change to negative because of the power that negative x would be raised to. So our general term here would be negative 1 to the n x to the n over n factorial. All over 2. All right, ladies and gentlemen, what happens? What happens when we add these together? The odd ones cancel, right? We have 1 plus 1 is 2, but then x minus x. Then we have 2x squared over 2 factorials. And, okay, and then what would our next term be? 2x to the 4th over 4 factorial, right? Okay, so what do we have going on here for our general term? Our general term would be 2x to the what? 2n over 2n factorial. Okay, we're dividing by 2. So then all of those get divided by 2, right? 1 plus x squared over 2 factorial plus x to the 4th over 4 factorial. And it's as easy as dividing that general term as well. Okay? Now, here we did see a time where we had to figure out the pattern to adjust our general term. That will happen sometimes, especially if we're like adding 2 together, okay? But a majority of the time, you'll be able to just use rules of exponents to adjust that general term. Okay? Please do your book homework. Tomorrow, yes, we'll have work time with the worksheet to get this really hammered down for your quiz on Friday, test next week. Hold on, I'll get it back. I'm just stopping this.